Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. We rarely think of speech as a physical workout, but the process of vocalizing is a complex ballet of muscle tension, kinetic friction, and rapidly shifting aerodynamics. And where there is movement, friction, and energy transfer, there is heat. Today, we map one of the most subtle yet critical phenomena in human biomechanics: the glottal heat sink, and the minuscule thermal anomalies that talking creates. For centuries, we analyzed the mechanics of speech using acoustics and fluid dynamics, how air moves through the throat and mouth to create specific sound waves. But a hidden layer of data exists within the infrared spectrum. Researchers utilizing advanced, high-resolution infrared thermography, or IRT, are now able to detect thermal shifts as small as 1/10 of a degree Celsius across the mucosal surfaces of the vocal tract during speech production. When you speak, the primary heat source is the glottis, the opening between the vocal cords. These cords vibrate hundreds of times per second, from about 100 Hz for a deep male voice up to 1000 Hz for high female pitches. This rapid, high-frequency vibration transforms kinetic energy into thermal energy. Think of it like a micro-oscillator constantly rubbing. Furthermore, the turbulent airflow associated with pushing air past constricted passageways adds frictional heating. If this generated heat and resulting moisture loss weren't managed, the delicate tissues of the vocal cords would dry out and become rapidly fatigued. This is where the surrounding physiology acts as the glottal heat sink. The rich vascularization and moist mucosal lining of the pharynx and larynx are designed to quickly absorb this localized thermal energy and dissipate it. It's a continuous, tiny heat exchange system designed for efficiency. Mapping these thermal anomalies provides remarkable insights. Researchers have found that the type of sound being produced dramatically alters the thermal footprint. For instance, high front vowels, like the E sound in sheep, require a more precise and constrained positioning of the tongue and higher tension in the vocal cords. These sounds consistently show a higher localized temperature spike in the glottal and pharyngeal regions than, say, the low back vowel, ah. When a person engages in continuous, loud, or complex speech for an extended period, the thermal map changes from discrete, momentary spikes to a more generalized, saturated warming of the entire vocal tract. This shift marks the beginning of vocal fatigue, indicating that the heat sink mechanism is reaching its capacity. The real power of mapping these tiny thermal anomalies lies in clinical applications. In professional vocalists, public speakers, or teachers, anyone who relies heavily on their voice, vocal fatigue is a major occupational hazard. Traditional methods for assessing vocal strain often rely on subjective self-reporting or invasive endoscopic examination. IRT offers a non-invasive, objective metric. A healthy vocal system produces symmetrical and predictable thermal patterns. However, if there is vocal cord swelling, inflammation, or the onset of nodules, the system becomes thermally asymmetrical or inefficient. The strained cord might produce an exaggerated thermal signature due to the increased mechanical effort required for vibration, or the heat dissipation might become localized and inadequate. Imagine a singer practicing for hours. By monitoring their thermal footprint in real time, coaches could identify impending fatigue long before the singer subjectively feels the strain, allowing for intervention, rest, and preventing long-term damage. It transforms vocal training from an art based on auditory feedback into a precise science based on thermodynamic efficiency. Furthermore, this technology is leading to new designs in professional vocal equipment. Microphones and headsets used by broadcasters or call center agents can be optimized not just for sound quality, but for how they might subtly affect the microenvironment of the face and throat, ensuring optimal thermal and moisture regulation to prolong vocal endurance. The Glottal Heat Sink reminds us that the human body is a masterpiece of complex energy balancing, even in the simplest acts like talking. Every whisper, every shout, generates a measurable thermal signature, a thermodynamic footprint that scientists are just beginning to decode, unlocking profound secrets about our vocal health and physical limits. For more incredible facts like this, don't forget to subscribe and turn on notifications.